Hello, my name is Alan Jones. I'm a principal software engineer in the Azure Incubations team at Microsoft and a maintainer of Drasi, the open source data change processing platform. Today I'm going to be talking to you about how to build change-driven solutions using Drasi. So what are change-driven solutions? Well, they're software systems that do something when data, usually from a database or other stateful system, that's important to that solution changes in some kind of meaningful way, or sometimes when the data doesn't change as the solution would expect it to. So let's see an example. In this scenario, we're going to talk about a retail organization that's trying to implement a curbside pickup capability. They want this so that customers can place orders online or via phone and then drive down and pick up the order without having to come into the store. So they've got two use cases in mind. Firstly, when an order is ready and the pickup vehicle has arrived, they want the system to notify staff so that they can take the order out and deliver it to the waiting customer. Secondly, when a vehicle associated with an order has been waiting longer than 3 minutes and the order still isn't ready, they want the system to notify staff so that they can expedite the order or update the customer with a more realistic wait time. So if we look at these two use cases through the lens of a change-driven solution, in the first case, the data that's interesting to the solution is the status of the order and the arrival of a vehicle associated with that order. Only when the order is ready and the vehicle has arrived should the system do something. And what should it do? It should notify staff. How would it notify staff? It might update a dashboard, or it could update some other specific user interface, could send a message, whatever the store decides to do. In the second case, the relevant data is, again, the status of the vehicle. But in this case, the vehicle has arrived, but the system should only do something if the order hasn't been fulfilled after 3 minutes. So in that case, what does the system do? Again, it notifies staff using whatever mechanism they've decided, like a dashboard or a message. So as we look at think more about the technology involved, the customer has an existing retail operation system through which they do order tracking, customer management, etc. And we can imagine this is in a PostgreSQL database. They've been using it for some time. To introduce this new curbside pickup capability, they've got this new physical operations system. And this could be camera-based, so it could do detection of license plates as cars drive into certain parts of the car park. Or it could just be text-based, so the customer is texting the system and telling the system that they've arrived. We will imagine this system uses MySQL. So if we look into what the data within these systems might be, when we talk about the retail operations, the central concept is the order. And then for orders that have been associated with this curbside pickup capability, there's going to be an order pickup record, and this is going to associate the order with a driver. And then that driver is going to have a driver name and license plate for the car. In the physical operation system, where the central concepts are vehicles and the zones where those vehicles are detected or registered as being. So you can imagine a zone could be the curbside pickup zone, and the vehicle would be identified again by its license plate. And the use cases we've talked about require us to connect the order and the vehicle. So we do that through the driver that's associated with the order and the license plate number that's associated with that driver and the license plate that's detected in the vehicle. And of course, there's no join between these two systems. So we're going to have to figure out how to connect those together as part of our solution. So I'm going to jump into showing you an example of such an application running. The example I'm going to show you is actually one that's available as a tutorial about how to use Drasi on our Drasi website at these links in this slide. So I'll jump into the demo and we'll go through it. So this is the curbside pickup tutorial page on the Drasi documentation site. You can see by the menu structure on the right-hand side, it's quite extensive. Begins with an overview of the scenario like we've talked about already. Talks through traditional approaches that one would use to implement a change-driven solution for this scenario without using Drasi. And then it has a step-by-step tutorial for how to implement the curbside pickup scenario as a change-driven solution using Drasi. Now, I'm not going to go through this tutorial here. We'll talk more about it later, and I'll show you how it's implemented using Drasi. But what I want to do right now is really show a simple example of a working change-driven solution, so you really understand what we mean by a change-driven solution, and show you a good example of what we are after, and also an example of what we're not after. So let me minimize that. This UI is what you build in the tutorial. At the end of the tutorial, you'll have this built out. It's got 4 sections. I'll just run through them quickly. On the bottom left, the retail operations is a simulator for the order management system. So you've got a bunch of orders that are in preparation, a list for orders that are ready for pickup, and simply by clicking the buttons on the orders, you can change the status from in preparation to ready. And all this is doing is it's updating a field for the order in a database, and I'll show you that in a moment. On the bottom right is the physical operations. This is managing the vehicle tracking system, where we've got vehicles in a parking lot and the vehicles that are in the curbside zone. Similarly, we just click to move them from the parking lot into the curbside zone and click to move them out again. And again, all that is doing in the background is updating the vehicle record for the zone that they're in. Top left is the dashboard, which tells staff that an order is ready and the vehicle is waiting. And on the top right is the dashboard that is telling staff that a vehicle has been waiting for too long. So if we look at, let's say, we'll put order 1 is ready for pickup, and the vehicle for that order is A1234 as its plate number, and then we put A1234 in the curbside zone, you should see the ready for delivery dashboard updated with that order almost instantaneously, and there we go. So up there we can see that that's ready. Now if either of the conditions of the order being ready or the vehicle not being in the curbside zone become untrue, then we would expect that order to leave that delivery list, and we can see that that is true. As soon as I remove either the order or the vehicle from the list, the delivery record disappears from the list. Okay. On the top right, this is the list of showing vehicles that have been waiting too long. So if I now put this red car, B5678, in the pickup zone, and we wait for around 10 seconds, what that is going to do is it's going to say that that car has been waiting too long, and it's going to put it in that the extended wait times list, so staff can now investigate the order or talk to the customer. And as you see there it appeared after that delay. If I move it out of here again, it disappears instantaneously from that list. So I'm going to open up a database editor now, so that we can see what's actually sort of happening in the background. So you can see here, this is just a plugin to Visual Studio Code, which lets me view and edit data in a database. So I'm looking at the orders database, and if we just refresh this, you'll see that here's the list of orders, and that tracks with the orders that are in that screen behind that we looked at before. And when I clicked one of these orders, it appeared in the ready for pickup list, and then if the vehicle was also updated into the curbside zone, the record would appear in the delivery list. Now, the bottom 2 sections are not implemented using Drasi, and the top 2 sections are using Drasi. So the bottom sections rely on the UI actually updating the information itself and being the source of that change. So if we look at changing one of these orders, let's choose order 1 again, and you can see I'm going to change this to ready, and I will save that change. I will save that change. And so that's written to the database. But what we notice is that this list of orders that are ready for pickup hasn't changed. So this is an example of not being a change-driven solution. So this data here, the data in the database has changed, but the UI hasn't updated to show that that's true. But if I now go in to the vehicles table and I take the vehicle for the order that we just updated and I'll change it to being in the curbside, and then I push that change, what we see is now that the vehicle and the order have been updated in the database, the vehicle or that order appears in our ready for delivery list automatically. Like, I didn't do it through the user interface. And you'll see, just to make the point, that neither of the lists of vehicles or orders are accurate anymore because they haven't reacted to the change in the underlying database, even though the dashboard, which is written using Drasi, has. So here we've got an example of bad change-driven solution behavior because things are not kept in sync automatically, and desirable behavior because the change is propagated through the system from the database change directly and automatically. So let's reset these so that the UI is in sync again. So set it back to parking, and you will see that the order disappears from the delivery list. And we'll go and fix this guy. Preparing. Okay, so now we should see that our UI is happy again. And so I've just used the UI to push order 1 back into preparation. And if we now refresh the view of the database, you will see that in fact that order, that's what happened. When we moved it across, it moved into a ready state. So the UI and the database are now back in sync again. So looking at the other dashboard, if I now take one of the vehicles, I'll refresh this again, so we've got up-to-date data. So looking at vehicles, if I pick one of these, let's say the Toyota, and I'm going to put it in curbside, and I push that, save that change. So we don't see any change immediately, but after 10 seconds, we will see that vehicle appear in the extended wait times list because its order is not ready, and there we go, it's appeared. Now if I take that out again and put it here, immediately it gets removed from that extended wait times list because the vehicles are no longer in the curbside pickup zone. So hopefully, based on that, you can see the desired behavior that we want. When data changes in a database, we want our solution to know about it and to be able to respond to that without relying on intermediary systems, UIs to do that checking and to do that activity. And now with that, I'll jump back to the deck. So from that example, hopefully you can see that change-driven solutions, systems that respond when relevant data changes in a meaningful way, are everywhere. Here's a few more examples. Imagine a building management solution that is able to control HVAC settings based on the occupants of a room. So as people move from one room to another, the system would update the room to bring it to a comfortable environment for each person. Or imagine a risk management system that is monitoring events that are happening in the world and notifying employees and their managers when a serious event occurring near the employee is putting that employee at risk. Or imagine an observability solution which is able to monitor a Kubernetes cluster for when a image is deployed to that cluster and check it against a list of known vulnerable images or disallowed images and notify operations to take it down, or even automate the immediate termination of the node that's running the image that shouldn't be running. Or imagine a solution that is able to monitor devices such as freezers that haven't produced telemetry data in a period of time and raise a ticket for someone to go and check on that device. So these are all examples of change-driven solutions where you want the system to do something in response to some meaningful change in some data, or for when data isn't changing as expected. So given that these systems are everywhere, how do we build change-driven solutions today? Well, at the heart of every change-driven solution is some data. So in this diagram, we've got representation of systems, IoT systems, applications, etc. They're all operating through some form of function, a microservice, service, which are writing data to databases or updating systems with configuration, and these systems are all generating telemetry data. And a lot of these services have been written to also output streams of change events that might be interesting to a change-driven solution. So our options in these days, in general, are polling. And polling is a solution that, almost everyone faced with building a change-driven solution the first time, they sort of fall into the pattern of, I'll just poll the database. What could be wrong with that? So they poll and they get the data back, and only then do they start to realize that there's more to it, right? They've got to poll periodically. How often do you poll? Because that's a trade-off between the currency of data and the load that you're putting on the database. Once you've done your poll, you've got to store that version of the data so that you can compare the next poll with it to see what's actually changed. So you've got systems that you need to keep some process running or run it periodically. You need to have a state store. And then you need to figure out how to do something when you've identified a change. And this could be, you push data down some messaging infrastructure, or you call some external process. But there's a bunch of work to do. It becomes quite complicated fairly quickly. So going beyond simple polling is the idea of processing a stream or a change log. So many databases produce change logs, and to detect changes in data, this is a very common pattern. People start hooking that change log and looking for changes, but the kinds of use cases we've talked about so far have been more business orientated. The idea of knowing when an employee is at risk because an incident's near them. This requires connecting data across multiple sources, and the change events you get in a change log are very low level. So mapping those low level changes to the high level business goals can be quite tricky. Also, once you've got multiple sources involved, you have to maintain state, and you have to maintain that mapping, and you have to manage a whole stream of data and events from the source, from the database or from the service that's generating the data. Most of these events are unlikely to be relevant, so you're having to sift through the whole stream of data just for the changes that are meaningful to you, and then do all the work to store state and determine if things have actually changed and map it into the high level business concepts. And then you need to figure out what to do with it. And again, maybe we send off some message that something downstream can hook into, or we activate some process. Again, it becomes complex. It's complex to build. It's complex to maintain. Another option is to use some kind of analytics platform. And there's a couple of challenges with these. One is that they often require you to load a copy of all your data into the analytics platform. So you've got that whole process that's going on. That introduces some kind of lag, usually, between the events happening and the data being available to process. And often these analytics platforms, they're built for analytics. They're built for going through, processing large amounts of data, looking for insights. They're not really designed to detect in near real time that changes have happened. So there's a cost associated with these, because you need the platform, you need to get data into the platform, and then you need to write these jobs that simulate the kind of activity that you want to detect near real time changes. So overall, all of these options for building change-driven solutions, as we've described them, are there's a lot of overhead, there's a lot of complexity. Change-driven solutions built using Drasi are simpler, making them easier to implement and easier to operate. Drasi consists of 3 simple components: sources, continuous queries, and reactions. I'm going to dig into each of these later and show you examples, but for now I'll just give you an overview. Sources provide connectivity to upstream data sources that you're going to use to drive your change-driven solution. This could include databases, whether relational or graph, stateful systems like Kubernetes and cloud platforms, or messaging infrastructure like Kafka, Event Hub, Event Grid, Event Bridge, that services and microservices often use to propagate events indicating that important things have happened. Continuous queries, as the name suggests, are perpetually running queries that operate across the data coming in through the sources. And they allow your change-driven solution to determine that something relevant and meaningful has happened for which the solution should do something about. And finally, reactions are what allow your change-driven solution to effect that action, to do something. And these allow you to integrate with downstream systems, such as writing to databases, sending messages down messaging infrastructure, sending email. And these are both, sources and reactions are both extensibility points in Drasi. So if the set of sources and reactions don't do what you want, you can easily write your own and contribute to the community. So Drasi manages to achieve this simplicity because we focused on generalizing the problem of detecting and reacting to change. And we built Drasi on a well-defined foundation of set-based change semantics and a consistent representation of change. We identified 2 important patterns, the continuous query pattern and the reaction pattern that we use within Drasi. And we identified early on that we really needed to deal with the presence of change and the absence of change equally. So that's built into the system from the earliest days. And together, these factors allow Drasi to enable you to create change-driven solutions much more easily. There is no code required within Drasi. You only need to define queries and configurations around the resources that you want to deploy. It integrates really well with existing data sources and infrastructure via the sources and reactions. And we've got a growing library of these that allow you to integrate with lots and lots of existing infrastructure. To understand why Drasi is different to streaming technologies and to appreciate the value it provides, you really need to understand how Drasi models and represents change. And this, in our experience, is the most difficult thing for people to understand. But once they have it, the rest of Drasi just falls into place and it makes complete sense. So I'm going to walk through the approach we have taken to how we deal with and represent change. So first of all, we like to start with defining the objective. And often, this is a higher level business or operational requirement. For example, when an employee becomes at risk due to a serious incident occurring near them, notify them, their manager, and their HR representative. So this is similar to a case we talked about earlier. And if you dig into it a little bit, you can understand that it's quite a complex thing to achieve. We're trying to, there's almost certainly 2 or 3 data sources involved. We've got HR systems, we've got risk management systems, we've got facility systems, and we need to bring all that together to achieve this high-level goal of notifying people when there's an incident happening that's putting them at risk. Okay, so we start with that goal in mind, and then the next thing is, how do you identify the set of things that you really need to watch for? And in this case, the set of things is the set of employees with their manager and HR rep, whose current location is the same as an active serious incident. So it's really phrasing that goal as a question, or really as a query. So if you're familiar with query languages, this will feel like an English language form of a query. Okay, queries produce sets of results. So the next thing is to understand that the transitions in and out of that set now have meaning. Right? So membership of that set means you're at risk, and not being a member of that set means you're not at risk. So the transitions mean that as an employee is added to the set, that employee is now one of the at-risk employees, and as employees are removed from that set, the at-risk employees are no longer at risk. So with that in mind, that we know the set of things and we know what transitions in and out of that set mean, every time that set changes over time, we can describe that change as a diff to the set. So what was added or deleted, and what was updated in terms of what did it look like before and what did it look like after. This then gives us the foundation on which to take data, use a continuous query to define that set of things we're interested in, consistently keep that set up to date, recognize when things are coming, when transitioning in and out of that set, and then notifying the reactions that these changes have happened in a consistent format as a diff, and allowing the reaction to take an appropriate action based on whatever the purpose of the change-driven solution is. So as I said, this can take a while to get used to. It's easier if you've got some experience writing and working with database queries. But I'm going to try a visual representation of this to really, hopefully, cement it in your minds. So we're dealing with the same problem. We've got this idea that we want to notify managers, employees, and HR when people become at risk. So becoming at risk means joining that set. So here we've got a set of employees that are not at risk on the left, they're grey, and a set of employees that are at risk on right in that red set there. So when an employee moves into that set from the not at risk to the at risk, the diff that comes out of there is saying we've added this employee at this point in time. Now, if employees move from that set, and given our requirements of it's an incident that's serious near them, what could move someone out of that set could be one of many things. It could be the incident has been resolved or it's been downgraded from serious. It could be that employee's location is now known to be somewhere else other than near the incident. It could mean that the employee's left the company. Like many of these things could cause that set to change. And the beauty of the continuous query approach is that you don't really care what's causing them to be added to or removed from the set. Drasi's figuring that out for you. You're just writing the continuous query. But the diff that pops out when those employees are removed from the set is a statement saying these two employees have left the at-risk employees set, so they're no longer at risk. Okay? And then finally, it could happen that a change causes employees to be added to the set and removed from the set at the same time, and for employees that are in the set to be still in the set but maybe have changed circumstances somewhat. So the kind of diff that would pop out at that point in time would be a combination of an employee's been added, an employee's been updated, this is what they were before and this is what they are after, and then another employee has been removed from the set. So once we have this really well-defined approach to representing change, we can construct or establish this continuous query pattern on top of that. So you can see on the left-hand side of this diagram, we've got various sources, and each of those sources will be pushing changes into Drasi, or the sources will be pulling changes from the data sources and pushing them into the query engine that we have running at the center of Drasi, and it's pushing low-level changes. This record's been updated, this record's been deleted. And Drasi, the continuous query engine, takes those low-level changes, figures out from the query it's been given, and the indexes and results that it's maintaining, what impact those low-level changes have had on the result set. And then it proceeds to output a stream of these query result change events, which are the diffs that we just talked about in the previous slide. So now that we have this consistent query pattern that's running queries and outputting a standard format of diff that we know the meaning of based on the query that we're running, then reactions, we can establish this reaction pattern. So on the left there you see there's a continuous query. It's outputting this stream of well-formatted, meaningful change events that contain all the information about what's been added, updated, and deleted to the result of the continuous query. The reaction takes that and it implements a handler for things that have been added, things that have been updated, and things that have been deleted. And it takes an appropriate action based on what it knows the solution's about, the changes that have happened. And so, for example, in this employee use case that we're talking about, the add item handler is this employee's been added to this set. Therefore, I'm going to send an email to that person, or a text. I'm going to send a message to the employee, to the manager, and to HR saying, hey, we've got a new employee at risk. So this could be, maybe as simple as a templated email, and the reaction knows to use the new employee at risk template and just puts in the data that's coming from the continuous query. Whereas when an employee has been removed from the set, the deleted item handler might use a different template saying, hey, this employee is now no longer at risk from this incident. And that would then be sent to the employee and the HR and then the manager. So now that I've been through what Drasi is, the value it provides, and a bit about how it works, I'm guessing if you're still watching, you're probably keen to understand how you would actually build a change-driven solution with Drasi and why it's different than other techniques that people are using. So I'm going to revisit the curbside pickup use case that we looked at the very beginning of the presentation. And I'm going to go through how you would use the concepts of Drasi, the source, the continuous query, the reaction, to build a complete, functional, change-driven solution to meet the requirements of the curbside pickup scenario. So if we think about, on the left-hand side here, we've got the two databases, the retail ops, which is Postgres, the physical ops, which is MySQL. We're going to need, to begin with, a source for each of those. So we've got a Postgres source and we've got a MySQL source in our library of sources. We're going to need two continuous queries. One is looking for the set of vehicles that are mapped to orders where the order is ready and the vehicle is in the curbside queue. And I'm going to have another query called delay, which is going to be looking for vehicles that are associated with orders, but which have arrived in the queue and the order hasn't been made ready within 3 minutes of their arrival. So this is a absence of change use case. And then we're going to have one reaction. We're going to use SignalR to get the data from Drasi down to the dashboards that the customer is using for their server stuff. So we're going to have a SignalR reaction that's going to push updates out through SignalR down to user interfaces. So all up, we're going to need two sources, two continuous queries, and one reaction. And I'll go through them, the way you define them in detail. First of all, you're going to need Drasi to start using Drasi. So we've got two options. You can install it on a Kubernetes cluster, or you can install it in Docker. So the Docker install is currently intended for individual developers who just want to use Drasi, develop against Drasi without doing a full cluster deployment. If you want to do a shared environment, you would deploy it to Kubernetes. And we support AWS and Azure-based Kubernetes clusters. We also support Kind and K3s for sort of self-hosted and local development options as well. For either of those deployments, the process is very straightforward, and it's on the slide. The URL that's there takes you to our documentation, which gives full details of how to configure the environments that you need in terms of how you set up the Kubernetes in those environments. But once you've got Kubernetes installed, you get the Drasi CLI, which is also explained on the page link there, and then you just run Drasi init, and it will deploy Drasi and all its dependencies to the currently active Kubernetes cluster in your kubectl context. Docker is similarly easy. You just need to install Docker, get the CLI, and run Drasi init, but in this occasion you do --docker, and it will install on the local Docker. In either case, once you've completed those simple steps, you're ready to use Drasi. So there are three ways that you can manage your Drasi environment. There is a Drasi CLI, which is the one I've talked about so far, and that's at the link provided there. You can do everything through the CLI that you need to do. We also have a Visual Studio Code extension, if you're using Visual Studio Code, which integrates all the management of the Drasi resources into Visual Studio, lets you view the status of them, lets you do deployments, gives some context, sensitive information about whether the resources are defined well or not, and lets you interact with queries in an integrated way in Visual Studio. Each of these is underpinned by the Drasi Management API, so both of those talk through the API. And while we haven't put a lot of effort into exposing that as a accessible endpoint, it's there, and the link there is to the code. So if you really want to interact with Drasi through that API, you can look there. And obviously both the CLI and the Visual Code extensions are good examples of how applications would use that API to manage a Drasi environment. So what we're going to do to start, now that we've got Drasi deployed and we know how we're going to manage it, we're going to start with configuring two sources. And the link at the bottom is a link directly to the area in our documentation that covers sources, and it's like a menu area where you can access all the different sources. So we're going to be talking about a Postgres source and a MySQL source. So here I've got my two sources side by side. So I'm going to show you the configuration of both of them at once. So first of all, the one on the left is the Postgres for the retail ops, and the one on the right is the MySQL source. You can see that they're both YAML files, and if you're used to building Kubernetes resources, it looks very, very similar. So we followed a similar pattern. So the header for all resource types, sources, continuous queries, and reactions is quite similar. The API version is always v1 at the moment. And then you use kind to tell it what kind of resource it is. So in this case, there's sources. You give everything a name. So these names are, for sources, the names are the names that continuous queries will use to subscribe to those sources so that they get updates from those sources. Once inside that spec section, you're dealing with configuration that's specific to the kind of resource that we're dealing with, so a source. And the kind tells Drasi which kind of source you want. So Postgres on the left, MySQL on the right. If you were to develop a custom source, then it would have a name, you would register it with Drasi, and you would be able to use that in this property to instantiate sources of your custom type. Once you've defined which kind of source you want to use, all the information in the properties section is custom to that particular implementation. So in this case, these sources, the MySQL and Postgres ones, are very, very similar. So the configuration is almost identical. But if you had a custom source or a different kind of source that you're using, it would be different based on what you needed to provide to that source. So in here we have things like the connection properties. So the host address, port, whether to use SSL, etc. Now in here we have user and password. These are in clear text, but in reality you can use a Kubernetes secret, or we also support identity providers for both Azure and for AWS. So you can use a managed identity in this section to connect to an external resource. Here is the database name and the tables that we want that source to be making available to the continuous queries running in Drasi. So that's the entire configuration. What we do then is we're going to use the CLI. So we run this command here. Drasi apply is what you use to apply any kind of resource. So in this case, we're saying Drasi apply, the -f tells it you want to use a file, and the file we're going to use is the retail ops source YAML, and we run that, it deploys. We can use this Drasi wait command to block until the resource is ready, until the source is ready, or till that timeout value given with the -t is expired. So here we're going to wait for the resource defined in the given file, which is the one we just applied. So it will wait. When it returns, we'll deploy the next source. So here we just use the same commands. We apply the physical ops resource, and then we wait for it. So once those are done, the sources should be ready, and we can check that they're ready by using this Drasi list source command, and it will return a table similar to that shown at the bottom of the screen and show us that those are available. Now, if they're not available, it'll say false, and there may be an error. So if there's any errors that have occurred while the source is being brought up, or its configuration is broken, or it couldn't connect to the source it was trying to connect to, there'll be some error in here that will help you understand what needs to be changed so that you can start debugging and trying to fix that. So sources are done. We now need to do our two continuous queries. So the link at the bottom there is the link to the page in our documentation that discusses continuous queries. And continuous queries have a bit more configuration than sources, so I'm going to split them and do them one after the other. So we're going to start with the delivery query. If you remember, this delivery query is looking for orders that are ready and vehicles that have arrived and are in the curbside queue, so that the order can be taken out by a server staff and not keep the customer waiting too long. So you'll see we've got a delivery YAML. Again, it's a YAML file with a similar format to before. In this case, the kind is not source, it's continuous query, and its name is delivery. So the name of a continuous query is the name that is used by a reaction that wants to subscribe to that continuous query to get its results. Here, in this sources section of a continuous query definition, it's describing to the Drasi runtime all of the sources that this continuous query wants to subscribe to and identifying where across those sources the nodes and the relations that are used in the query come from. So if we look at one section at a time, this is saying this query needs to subscribe to a source called physical ops, and it's going to get nodes with the label vehicles from there. Next, it's also saying it wants to subscribe to the retail ops source, and the nodes it's going to get from there are the nodes with the label orders. So vehicles is coming from one database, orders is coming from the other database. What this is doing is creating a join between those two databases because there isn't a join in the data itself. And so this is telling Drasi how to join data dynamically as data is coming in. So it's saying for the vehicles nodes, use the plate property, and when the value is the same as the plate property in the orders nodes, assume there's a connection, create the synthetic connection here. So this is in the query property, this is the actual query that is running, that is building the set of things that we're interested in, and from which Drasi then can determine what's changed and propagate those change notifications about the membership of this query result or this set. So we currently support Cypher or OpenCypher. So all of our queries are written in OpenCypher. We are looking at other languages, and I'll touch on that towards the end of the deck. But I'm not going to fully go through Cypher. It is pretty intuitive to get started with, and you can still do quite rich, complex queries with it. So it's got a nice on-ramp, even if you haven't done much querying before. So this initial match clause is telling Drasi that we want to look for this pattern of data in our source data. So we want to look for orders that have a pickup connection to these vehicles. And this pickup relationship that exists between orders and vehicles is the one that we defined in our joins section over on the left-hand side. So, this is the dynamic relationship that we have created based on the plate property in orders has the same value as the plate property in vehicles. So if we find that pattern and then we look at the order, it needs to have a status of ready, and we look at the vehicle and it needs to have a location of curbside. So if all of that is true, those conditions are met, this set of data, this instance of an order in a vehicle, fall within our desired result set. So we assume, because they're in the set, that this is an order that we need to add to the result set and propagate out, saying that the order's ready and needs to be taken out. And the return clause is the projection of the result set. So now we're saying, okay, for anything that's in the set, this is what we want it to look like. These are the columns, these are the fields that stuff in the set has. So we can choose an arbitrary set of things here by just specifying the name, and we can rename them, as you see here, using as clause, and we can do some basic manipulation with some functions on this as well. But anything in the set is going to be propagated with that structure. So not only are you able to say, I want these things, but you can say, I want them and I want them to look like this. Okay, so onto the second query here, the delay query. This is in a delay YAML file. You'll see that it's kind continuous query, but its name is delay. It has exactly the same sources configuration as our previous query, because we're interested in the same set of data or the same source of data. But you'll see the queries quite different. So we do have the same match clause, but here the where clause is where the order status is not equal to ready. So we're only interested in orders that are not ready. And here, this is how we have managed to achieve the detection of the absence of change. We've introduced a number of custom functions into Cypher which allow us to fit our absence of change capability quite elegantly within the context of a query. So we don't have any extra mechanisms, it's just part of the query. And what this one is saying is that a property, in this case the location, needs to be curbside, and it needs to be that for So it says true for, it needs to be true for 10 seconds. So the use case says 3 minutes, but we did it at 10 seconds for the demo purposes. But you don't need to do anything else. You can just put this true for function in, tell it for how long something should be true. Drasi sets up all of the callbacks and all the timers that need to be put in place and manages the query. So when something first comes along into this result set and its status is not ready and its vehicle location is curbside, Drasi will start timing that. And once it's been true for 15 seconds, then it will get put into the result set. And therefore, we start to see this query being an observer of vehicles that have been waiting too long. In this case, we've got a return set which is much smaller than the one we had previously because we're interested in a less data set. Okay, so we've defined our two queries. We now, as before, we do Drasi apply for the delivery query. We do Drasi wait. Drasi wait is optional, but we'll do it here. Once that's finished, we'll do apply delay. So we're doing the deployment of the second query, wait for that one. And then just like we had Drasi list for sources, we have Drasi list for queries. And you get a table showing all the deployed queries and the current status of each. If there's errors, they'll be in here, so you can investigate them. Okay, so we've got sources deployed and we've got continuous queries deployed. So the only thing we have left is the reaction. And link at the bottom is the page in our documentation where you will find all the reactions that we have available and how to configure them and deploy them. So this is very, very simple. This is a signal R reaction. And what we have here is kind reaction. Then we have a name, signal R. Then we just say this is the type of reaction it is, in this case signal R. And then we just tell it what queries we want to listen to. And everything else is just the default. So very, very simple. And this will establish a connection with the signal R infrastructure and allow clients to subscribe to an endpoint, which is then going to get data pushed down at the results of our continuous queries pushed down it. So again, to deploy this, we do Drasi apply, Drasi wait, and again, we can do a Drasi list to see the status of the reactions and deal with any issues that may have occurred. And with that, you've seen the two sources, the two continuous queries, the one reaction, all just configuration, no code, they're all deployed, and everything's ready to go. So one thing that is very common in change-driven solutions is the need or the desire to keep some UI or part of UI dynamically up to date based on the results of a query. And this is true in our demo app. We've seen little dashboards that keep the display of orders that need to be taken out to cars or vehicles that have been waiting too long. So that's part of the solution that we have seen. And Drasi provides a really novel way of achieving these what we call change-driven UIs. So in that diagram, you'll see we've got our delivery and our delay query here. We've got which we've created already, and we've got our reaction, which we've also created. It's pushing the content, the updates from the queries out to signal R. Well, we've got two components that we've written, one for React, one for Vue. And what they do is you put them in your UI, your app, and they will dynamically keep the contents of that component up to date with what's the current result set of a continuous query. And you'll see on the bottom of the screen is the URL where these are described. It's all described as part of the signal R reaction because they use signal R as the transport mechanism of data to the client. But they are really easy to use, and the effect is quite powerful. So here we've got the React version. So on the right-hand side is the little dashboard that is showing orders that are ready for delivery to be taken out to clients. And on the left-hand side is the React code that is needed to keep the contents of that list up to date. So you'll see here, the result set is the name of the component that we've built. You give it the URL of the signal R endpoint where this component needs to attach to. You give it the query ID that you want to populate the list. So in this case, we're saying it's it's a variable, but it would be the delivery query. That would be its name. And then you just give it the template that you want applied to every element that's coming in through that connection. And the data, the structure of it coming in will be the structure of the what you put in the return clause of the continuous query. So that's the React. That's all you need to do for React to get a section of your UI dynamically kept in sync with the contents of a continuous query. Here's the Vue version. It's very similar. In this case, you're seeing on the right-hand side, this is the delay dashboard. This is the list of vehicles that have been waiting too long. On the left-hand side, again, you'll see that it's called result set. In this case, it's Vue syntax. So we've got the URL, and again, the query ID. In this case, it would be delay. And then you've got the template that gets applied to each of those items that comes through from the continuous query. And it's as easy as that. So hopefully you can see from what I've shown you that Drasi does indeed simplify the development and management of change-driven solutions. I've shown you that you can build the curbside pickup solution with 2 resources, 2 continuous queries and a reaction, no code involved, just queries and configuration. Drasi is intended to be a single platform on which you can run many change-driven use cases. So gone are the days when you would have to do a bespoke solution for each time you wanted to do some kind of polling mechanism or changelog processing for a given solution. So we're providing a general mechanism for which you can put the back end of change-driven solutions in place in shared infrastructure. We handle both the concept of change and, more uniquely, the absence of change, and we handle them in a consistent way, just through queries. And Drasi deals with all of the mechanisms that are needed to do that. We are multi-cloud and on-premise. Currently, we're focused on Kubernetes. We have the Docker version, which is more for development, but we are looking at other ways, other container environments through which we can create deployments that don't necessarily require you to have Kubernetes. And we have a lot of integration opportunities with a range of data sources and a range of downstream infrastructure for pushing the results of continuous queries out into a range of applications and solutions. If we don't have the sources and reactions that are needed in our growing library, we have SDKs across multiple languages that allow you to build custom sources and custom reactions and hopefully contribute those back to the community. Talking of the growing collection, here's what we currently have. So you can see there's a range of sources: Postgres, MySQL, SQL Server, Cosmos Gremlin, Dataverse, Kubernetes as a source which we touched on earlier on. For continuous queries, we are focused on OpenCipher at the moment. We have done a SQL experimental, added SQL as an experimental language support to try it out, see what would happen. We are currently working on GQL, the new ISO standard, to replace our Cypher implementation, and it's in development. And one thing I haven't touched on, but is part of the system already, is a middleware pipeline in a continuous query or pre-continuous query, so that you can do some data reshaping based on what the query needs or what would be optimal for the query that might be different from how the data is coming in from the source in its original format. And for reactions, again, we've got a collection of reactions. So we've got this idea of a SQL stored proc reaction, which covers Postgres, MySQL, and SQL Server. So you can do parameterized stored procedure calls based on the content of the changes coming from a continuous query. This allows you to keep databases dynamically up to date from the result sets of a continuous query. We have a Gremlin command, which is a similar thing, but for issuing Gremlin commands to Cosmos. We have multiple messaging infrastructure support. So for like EventBridge, Event Hub, SignalR, we've got integration with Microsoft Dynamics. And we also have a Debezium reaction, which allows you to push changes out into a Debezium pipeline so that it can feed into a CDC infrastructure. And with that, that's it for what I've got to show you today. But if you would like to learn more, then the link on the left is to our documentation site. The QR code will take you there as well. Here is our URL for our GitHub repo, our Discord channel, which is growing and active, and our email address if you want some more info directly from us. But we're all active on the Discord channel, so it's an easy place to get to us. And then the links on the bottom right are 3 links to the curbside pickup example that I've been talking about through the demo. So one is the fully worked tutorial, which can be run in a code space or a dev container or locally. And it's the documentation for it is also covers some comparisons with alternate approaches that you might have to do today if you didn't use Drasi. So there's a lot to learn from there, and it's a good place to start your Drasi journey, working through that tutorial. The code for that is fully available in our repo, in our learning repo, and the developer of that tutorial also did a video of it, him working through the whole thing, and has put that on YouTube, which is a great resource if you don't want to work through it yourself and you want to see how it's done. And with that, I'll thank you for your time, and I would love you to get involved and come and join us in the Drasi community and help make it into an engaged and vibrant community to build Drasi so that we can all make change-driven solutions much easier. And with that, I'll say goodbye. Thank you very much.